this video, I will discuss the solutions for numerical problems 5. The first question, determine the lime and soda ash dose in milligram per liter as CaCO3 required to soften the following water to a final hardness of 80 milligram per liter as CaCO3. The ion concentration in milligram per liter as CaCO3 are follows. So the concentration of Ca2 plus in milligram per liter as CaCO3 is 120. Then concentration of Mg2 plus is 30. Concentration of HCO3 minus is 70 and concentration of CO2 is 10. Okay, so we need to calculate the amount of dose of lime and soda ash which are required. So please refer to the slide chemical dosage, where particularly regarding the amount required for Mg2 plus is given. So basically the amount of lime required, okay, we start with first CO2. It is, so whatever the amount of CO2 is there, the equivalent amount of lime is required. So that is 10 milligram per liter for CO2. Then for HCO3, which is basically for the carbonate hardness, which is whatever amount, equal amount of lime is required. So 70 milligram per liter of lime for HCO3 minus. Okay, so then for magnesium we need excess lime. So the excess lime which is required depends upon the concentration, whether this concentration of Mg2 plus is less than 40 or between 40 to 60 or between 60 to 80 or greater than 80. Depending upon the interval, the concentration of Mg2 plus required, concentration of lime required, okay, for softening Mg2 plus is calculated. So since the amount here it is 30 milligram per liter, which is less than 40, so we can say it would is 20 milligram per liter. So this is clearly mentioned in the chemical dosage slide. So then plus 20 milligram per liter. So this is for carbon dioxide, then this is for carbonate hardness, and then this is for Mg2 plus excess, so which is 20 milligram per liter for Mg2 plus. So total 70 plus 10, 80 plus 20, so 100 milligram per liter of lime is required. Next, here further we need is the amount of soda ash required. So the amount of soda ash required depends upon the final amount of hardness, which is 80 milligram per liter. So first we have to find out final non-carbonate hardness. So the total hardness is the concentration of calcium and magnesium, so which is 120 plus 30, 150 milligram per liter, out of which carbonate hardness is only 70. Carbonate hardness is 70 milligram per liter. So total minus carbonate will gives us non-carbonate hardness. The non-carbonate hardness which is present is 150 minus 70. So total 80 milligram per liter non-carbonate hardness is present. But we don't need to remove entire non-carbonate hardness because we have provision of, the final hardness we need to keep is up to 80 milligram per liter. The issue is we always try to first remove the carbonate hardness because removing non-carbonate hardness is expensive. So, but thing is, for removing non-carbonate hardness, there is a limit. So maximum or the minimum which you can keep, minimum carbonate hardness that present irrespective of whatever method used because of the solubility of the carbonates is 40 milligram per liter. So this much carbonate hardness will be there even if you separate the carbonate hardness. So since you want to have finally 80 but 40 milligram per liter will go to carbonate hardness, so non-carbonate hardness that can be present in water is total that you can keep, which is 80, minus that which definitely present due to solubility is 40. So which means 40 milligram per liter is the non-carbonate hardness finally you keep. Then what is the initial non-carbonate? This is the initial non-carbonate hardness. So this is initial non-carbonate hardness and this is the final non-carbonate hardness. So non-carbonate hardness that is removed is initially 80 milligram per liter minus the final which is 40 milligram per liter, so which is 40 milligram per liter. So the amount of soda ash which is required would be equal to non-carbonate hardness to be removed. So soda ash required soda ash would be 40 milligram per liter. So this is required soda ash and this is required lime. Okay, the next question. Find the terminal settling velocity of a spherical discrete particle with diameter 0.5 mm. and specific gravity 2.65. Settling through water at 20 degrees Celsius with laminar flow condition. Given that density of water 1000 kg per meter cube, and viscosity of water 0.001 Newton second per meter square. So this is direct substitution problem in the terminal velocity equation. So terminal velocity Vt is equal to G into density of particle minus density of water into diameter of particle square divided by 18 mu. G is acceleration due to gravity, that is 9.8. Density of particle density is given in terms of specific gravity, that is 2.65. So in kg per meter cube if I take, then it would be 2650 minus density of water 1000 into diameter of particle 0.5 whole square, that is 0.25. This is given in mm, so this would be 10 power minus 6 meter square divided by 18 into 0.001 Newton, so it's 10 power minus 3. So if you just substitute all the values, you should get around 0.224 meters per second. This is the terminal settling velocity. The next question. A rectangular sedimentation tank is treating 2.5 million liters water per day. The size of the tank is 17.5 meters into 5.5 meters into 3.5 meters length, breadth and height. So if 80 ppm suspended solids are present in water, assuming 75% removal, in the basin, and the average specific gravity is 2.0. As 2.0, determine the following. Average velocity of flow of water, detention time, amount of solids deposited, overflow rate. Okay. So given the flow rate, that is 2.5 million liters per day. So that is Q is equal to 2.5 into 10 power 6 liters per day. Or you can say 2.5 into 10 power 3 meter cube per day means 24 hours, meter cube per hour. So first question is average velocity of flow of water. So average velocity can be calculated as the average is equal to, average velocity is basically the velocity in the horizontal direction. So it is given by volumetric flow rate divided by the cross sectional area. Basically if there is a flow in this, so this is the cross sectional area, this is the cross sectional area, so we divide that Q by cross sectional area. So what is the volumetric flow rate? That is 2.5 into 10 power 3 divided by 24 hours means 24 into 3600 meter cube per second. This we have to divide by cross sectional area. So cross sectional area, the dimensions are length dimension 17.5, breadth dimension this is 5.5, and height is 3.5. So this 3.5 and 5.5 contribute to the cross sectional area. So 3.5 into 5.5. So if you calculate this, you should get 0.0015 meters per second. The next question, detention time. Detention means how much time a sample of water present in the tank. So it is given by detention time. It's basically volume of the tank divided by volumetric flow rate. You can also say it maybe length of the tank by the average velocity also. Okay, so volume of the tank by volumetric flow rate. So what is the volume? 17.5 to 5.5 into 3.5 divided by volumetric flow rate. It is 2.5 into 10 power 3 meter cube divided by 24 hours. So this is, if you calculate, you should get around 3.23 hours. Third question, amount of solids deposited. So what we have is 80 ppm suspended solids. 80 ppm suspended solids. Out of 80 ppm solids, 75% are being removed. So to calculate volume of solids deposited, should be nothing but concentration 80 ppm parts per million, that is 80 by 10 power 6 into the flow rate. Flow rate is 2.5 into 10 power 6 liters, or you can say 10 power minus 3 meter cube per day. So which is nothing but roughly 0.2 meter cube per day. So this much volume of solids are being deposited. So to calculate mass of solids, then mass of solids deposited, out of which only 75% is being deposited, into 75%. So if you calculate this, you get around, I think 0.15 meter cube per day. Okay, so this much value means how much is the mass. So just multiply with the density. So we get, given the specific gravity as 2.0, so 0.15 meter cube per day to density is 2000 kg per meter cube. So this you should get 15 into 2, 13. So total should get 300 kg per day. So this is the mass of solids which are being deposited. Next is overflow rate. Overflow rate is volumetric flow rate divided by the base area. This base area. So Q by base area. Q is 2.5 into 10 power 6 liters per 24 hours into the base area is 17.5 into 5.5. So this is around 1082.2 liters per hour per meter square. The next problem is grid chamber problem. Fourth question. Design a grid chamber of maximum wastewater flow of 0.160 meter cube per second with the horizontal velocity of 0.2 meters per second, and it is given as a depth. It is also not exactly depth, it is width of 1 meter and a detention time period as 1 minute. Provide 0.3 meter for freeboard and 0.25 meters for accumulation zone. And 25% additional length. These two are for depth and this 25% additional is for the length, additional length, to accommodate inlet and outlet zones. To accommodate inlet and outlet zones. Okay. So what is given? The flow rate is given. Flow rate Q is 0.160 meter cube per second. Flow rate is given. Then horizontal velocity VH is given, which is 0.2 meters per second, and width is 1 meter. And detention time is 60 seconds. 1 minute means 60 seconds. Okay, so first, since we know flow rate Q, okay, and horizontal velocity V, we know that horizontal velocity V is Q by cross section area, that is Q by, this is width into height. So we can calculate height. H is equal to Q by width into horizontal velocity, that is Q is how much? 0.160 meter cube per second divided by width is 1 meter to horizontal velocity is 0.2. So this is 0.2, this is 0.8, so it is 0.8. So now height is 0.8 meters. Now we need to calculate the length. So as we know, what we have given here is detention time. We use that information. Detention time is volume of the tank divided by volumetric flow rate. Volume of the tank is length into breadth, okay, that is 1 meter into height, which is 0.8 meters, divided by Q, that is 0.160. So this value detention time is given, which is 60 seconds. Here this is meters cube per second. So if you can calculate L from here, L is equal to 60 into 0.160 by 0.8. So this should come 12 meters. So now we got length as 12 meters. It is given that we should take 25% extra length, which means 1.25 into length 12, which is 15 meters is the length of the tank. Then height is, we got 0.8 meters plus extra 0.3 meters freeboard plus 0.25 for accumulation zone. So total it would be 1.35 meters. That's it. Okay.